Okay. So, in the last class we looked at unification. Today we want to look at forward chaining again. So, remember that we had looked at this rule called modified modus ponens, which was like modus ponens, except that it uses unification because one may have variables inside the statements essentially. So, unification is used to make them the same, and then you can use the modified modus ponens rule to apply essentially. So, this modified modus ponens plus unification actually gives us a mechanism for able to reason. So, now let us focus on the task of reasoning itself as to which inferences to make essentially of the many possible inferences that you can make, which is the one that you want to make essentially. Now, before we do that, I just want to make a comment that as far as the knowledge representation part goes, the community which looks at these algorithms, or you might say the mathematical inclined community or the logic community, they do not focus too much on how you are representing things essentially. So, that is why we use variable names like predicate names like p, q, r. We do not particularly care what is the variable you are using. So, in some sense we are using ad hoc predicates. We are not giving any thought to the fact that whether these are the predicates which are the best ones to try to describe the domain that we are trying to describe, and so on and so forth. We will come back to knowledge representation at a later time. We want to focus now on the reasoning part essentially, okay, which is algorithms essentially. So, the reasoning part is concerned with algorithms. And we essentially want to focus on what is the algorithm that we want to use essentially. Now, what is the reasoning algorithm essentially? We are given some knowledge base, so we will use the term KB as usual for knowledge base, and a goal or we can call it a query alpha. The question we are asking is, does the knowledge base entail alpha, and then we are actually translating this question to a different question. So, now we have gone past the semantics to does the knowledge base derive alpha essentially. So, if you try to imagine what is the situation here, pictorially you might say that this is a knowledge base and it contains many statements. So, as far as the abstract representation or the logical representation is concerned, we are not making any statements about how these things are stored, how they are retrieved, and any such thing essentially. So, we just have a collection or a set or a sea of statements, and then we have a collection of rules. In our case, we have let us say one rule which is modus ponens, modified modus ponens. You could have more rules, that does not matter, and we are given a query alpha, and we are asked whether this alpha is true or not essentially. And we want to generate a proof essentially. What is a proof? A proof is a sequence of conclusions at the end of which the last conclusion is alpha essentially. So, that is a direct proof or the forward chaining method that we are looking at essentially. So, somehow from this sea of formulas we have to pick the right rule, apply it to right facts, and generate some new things essentially. So, for example, we may pick this and we may pick this, and we may add another thing to the knowledge base, then we may pick this and we may pick this, and we add another thing to the knowledge base, and so on. We keep adding more things, the knowledge base expands, and at some point hopefully we will add this alpha essentially. Now, if you look at the two different communities, the logic community or the mathematics community. So, a logician will simply say a proof exists. Or they might even produce a proof essentially. So, they do not tell you how they arrived at the proof, but they will say here is a proof. So, your task is now to simply validate or verify that the proof is correct or not. So, you basically check whether every inference is sound, and if that is the case then you accept the proof essentially. But as a computer scientist, which is what I presume all of us are, our task is to find the proof. The logician or the mathematician does not give you the process through which he or she arrived at the proof, whereas when we are writing programs to find proofs, then that becomes our primary goal essentially. How do we find a proof essentially? So, this exercise, as I might have mentioned, is called theorem proving. So, we use the term theorem to stand for any true statement essentially. So, because that is what mathematics says, that once you prove something it becomes a theorem or a lemma or whatever. And the task of theorem proving is to find an algorithm which will find a proof essentially. So, find a proof. There may be more than one proof. So, but at least you can find one essentially. So, the question of course is how, and the answer to that is some kind of search. Okay. So, at a high level we have already said that the algorithm is as follows: pick a rule with matching data, antecedence is the left hand side of the rule. So, if something that something is the antecedent. So, if you can find a rule which has those parts present in the knowledge base, then we add consequent to the knowledge base. So, antecedents are in the knowledge base. So, in this way we keep adding more and more statements to our knowledge base, and we will terminate when we have added the statement that we are interested in, the thing that we call alpha essentially. So, the question is what kind of search can one employ? So, what do we have? We have a set of rules in this, we may have one or more rules, and we tend to distinguish between two kinds of things. One which we say are facts and the other are rules. This is just a distinction that we use from the point of view of devising algorithms. Both are statements in logic. But we distinguish between facts and rules. So, fact for example, may be man Socrates, and the rule may be for all x man x implies mortal. So, I will just use m here, or let me write. So, we distinguish between these two kind of rules. So, essentially what modus ponens, which is one rule of inference we are using, has access to a large collection of rules like things all men are mortal, all students are bright, or all bright students are girls, and things like that. Whatever statements that we have, we will call them as rules, and whatever facts we have are is the actual data in the knowledge base essentially, that Socrates is a man and Shrestha is a student and Shrestha is a girl, and this kind of statements are facts essentially. So, modus ponens is trying to pick a rule essentially. So, when we say rule here, we mean that is a statement that I mean here. These are also statements in first order logic. Okay. So, there is a slight confusion between rule of inference and rule here. Rule of inference is modus ponens or modified modus ponens. It is a meta level thing. Rule in the language is basically universally quantified statements, things like this, that all x's are y's and things like that essentially. So, the algorithm now needs to wade through all the rules and all the facts to find something which is a matching piece of rule, a statement which is a rule and a matching statement which is a fact essentially. Now, you can see that if you have a large knowledge base, then the choices that you may have will be in proportion to the number of facts you have and the number of rules that you have in your statement. So, it is a problem which is going to increase combinatorially in terms of complexity. So, that is one of the main issues that we want to address essentially. So, what are the kind of search algorithms that we can think of? One is of course, the simplest search is linear search, right, is linear or sequential. It simply says take the first rule, try to apply it to the first piece of data, try to match it with the second piece of data, and so on and so on. So, you take the rules one by one, then you match them with data one by one, and so on, you keep doing that. We will come to this later essentially. This kind of an approach is actually used in a language Prologue. And when we come to this, we will see that because we are using an algorithm which is sequential search, the onus will be on the person who is writing the knowledge base or who is writing the rules to put them in a certain order, so that the algorithm will find the solution quickly essentially. We will come to Prologue, which is actually a process of backward chaining as opposed to forward chaining that we are looking at, and Prologue uses sequential search. So, we will come to that a little bit later essentially. So, today we want to see how forward chaining can be made more efficient essentially. So, we want to try to look at that aspect. So, what is forward chaining is doing is the process that we are saying, look for a rule, look for matching data, add the consequent, and then keep doing that essentially. Now, let us assume that rules are given to us in a particular format, which is so when I say rules, I mean rules which are also statements in the language, or statements of the kind if antecedent 1 antecedent 2 let us say there are n conditions on the left hand side, then consequent. So, we are given a collection of such rules. So, when you look at all these rules, we will have a set of patterns essentially. So, the patterns that we are trying to match are the left hand side of the rules. We are trying to see whether there is some element in the knowledge base which matches antecedent 1, some element which matches antecedent 2 and so on and so forth essentially. And we are given a set of rules. So, let us say that our knowledge base looks like this. A11. So, A11 I will use as a notation to stand for rule 1 and antecedent 1. But I may have other things. So, I may have A12 then so on A1n. So, these are the n incidents and that I am talking about. Then I will have A21 and so on A2r, let us say it has got r antecedents and then so on and so forth essentially. So, for every rule I will have certain number of antecedents. So, I will have a whole list of patterns that I am trying to match essentially. And what am I trying to match? So, I am trying to match facts, right. So, let us say simply facts are some statements, data point 1, data point 2, data point 3, some number of data points we have essentially. In the terminology that we will look at of forward chaining algorithms that we will see, these facts are also called working memory elements. And this or the facts are essentially called working memory, and each of those data items is called a working memory element essentially. So, what is the task? The task is you match A1 with D1, then you try and match A1 with D2, match A1 with D and so on and so forth. So, you can see that the total number of matches that we will have is that if we have n antecedents on the average per rules, if we have let us say r rules and d data elements, then we will end up matching every antecedent with every data element essentially. So, n into r into d matches. So, this scenario is a little bit different from what I started by saying. I started by saying pick a rule with matching data, but actually now I have moved to a slightly different way of doing things, which is the method that is used in what we call as production systems. Or rule based systems. In the 1980s, they would be called expert systems. And what a production system does is that it has something which is called an inference engine. This is the terminology which this particular community uses. Inference engine is simply the algorithm that we are talking about, which says that find a matching rule, add the consequent and so on and so forth. But the difference is that a typical forward chaining inference engine is made up of 3 steps. The first step is match, and the thing about this is all pairs of the kind some rule r I with matching data point. So, D 1 1, D 1 2, D 1 n, let us say. Find all such pairs. Let me emphasize that. So, the match part of the algorithm simply says, given a set of facts and given a set of rules, both are statements in first order logic, which rules are matching with which data, produce the whole set for me and I will choose which one to select after that. So, we have sort of doing a pre processing of match essentially, and this match is what will do this NRD number of matches essentially. Now, that we have done all the matches, we have a step called resolve, which essentially says choose a pair. Obviously, it is very critical as to which one you are choosing. So, this element of resolution, what is the problem solving strategy that you are trying to use, as to which rule you will apply, we will come to this a little bit later. So, at the moment I want to focus more on how to make this process of making inferences efficient, and the algorithm that we are looking at is essentially designed to do this match more efficiently essentially. The third step in this process is execute. Which is basically the step that we have, which is that you add the consequent to the knowledge base, or in this terminology add the consequent to the working memory essentially. So, the same thing we are doing, except that what we are saying is that we will do all the matchings first, then we will decide which one to actually apply essentially. So, the match component will find all the matching rules with the corresponding data, the resolve component will choose one of them, and execute will basically add the consequent essentially. So, that is the basic inference engine. It is a 3 stage process: match, resolve, execute, and this is put into a loop essentially. So, what happens is that it is a match which is the most expensive part. So, there is one small thing I want to state. Before we move on to match, this execute part, we have said it is add a consequent. To the knowledge base or working memory. And in terms of this notation that we are using, this consequent is also a working memory element. But in practice, these one allows So, not only do we add a consequent, but this, so we are in some sense deviating from classical logic essentially. We are devising a language or a system in which you are allowed to delete elements essentially. So, just give some thought to this, what is happening to this whole process essentially. Not only do you add new facts to the knowledge base, which means new rules may be triggered and so on and so forth, but you are also allowed to delete certain facts from the knowledge base essentially. So, the consequence of this what would be the consequence of this? That in the match has to be done in every cycle. What is the cycle we are referring to? We are referring to this cycle of match, resolve, execute. The consequence of the fact that you can delete elements means that something which may have been matching earlier will no longer be matching now essentially. If you are not allowed to delete elements, then we could have a simple strategy which says that do a match, okay, produce all the elements that all combinations of rule and matching data, this thing, pick one and execute it, which means you will add some more facts, just see as to those new facts which rules they may trigger. So, add that to the set that match produces. So, the set that match produces a set which looks like this, rule R followed by matching data as I said. So, d I 1, d I 2, d I n. This is called as a conflict set. This is just terminology, you should be aware of it. The conflict set is basically the collection of rules and matching data that the match algorithm outputs essentially. The consequence of the fact that we can delete elements is that this conflict set has to be computed every time afresh essentially. If we were not allowed to delete match, if you are not allowed to delete working memory elements or facts from the database, then once a rule and its matching data has entered the conflict set, it will stay there till it is executed essentially. But the fact that we are allowed to delete elements, working memory elements or data set means that even if a working memory element has or a rule and a combination of data has got into the conflict set, because we are deleting one of the antecedents, that rule may no longer be applicable essentially. So, it complicates the whole process. So, in principle we have to match all over again essentially. And it has been shown that match consumes 80% of the computation time. Even with optimizations that we will talk about, the match part really takes up all the time in the cycle of match, resolve, execute. Resolve is the most straightforward process and execute is of course constant time essentially. So, in the next class when we meet, we will look at a algorithm which is more efficient, which is called the rate algorithm. So, keep in mind that we are working in this match, resolve, execute paradigm where the execute phase may delete or add data to the knowledge base, and we want to basically make the next round matching process efficient. And in doing that, what we really want to do is to see how much of the match we can carry forward and try to do these kind of optimizations, which is what is done in the Rete algorithm, and we will see that in the next class.